Now in this lecture we are going to have a little bit of a revision, a little bit of an introduction if you haven't seen these things before, of ordinary differential equations, or so-called ODEs. Now in a basic course in calculus, the first kind of differential equation you see is a separable differential equation. Okay, and the word separable gives you a hint on the method of solution. So unfortunately there's no general way of solving every kind of differential equation. So we have to identify certain techniques, certain methods for certain styles of equation. Now, a differential equation is just like any other kind of equation. It has an equal sign and it has some unknown thing that you want to solve for. The difference with differential equations is you are looking for a function. You're looking for a function rather than a number. Okay? That's the big difference. Now, differential equations have a lot of important applications in modelling. Okay? Many basic equations can be recast under certain assumptions in the form of differential equations. Okay? And the power that we obtain when solving these equations is that we can make precise predictions about the model under consideration, about the future states or the past states. So that's the motivation. So separable ODEs, or ordinary differential equations, are of the following form. Now you'll see here I've got a dy dx and a function of x times a function of y. You can also call a differential equation separable if it's of the following form, say something like this. Okay, where you've got one function of x divided by another function of y, all flipped around. Now the way that we would solve these kinds of equations is just essentially a little bit of algebra and some straight integration. Okay, so in particular we separate the variables. So what do I mean when I say separate the variables? Well, let me give you an example. Let's solve this particular differential equation down here. Okay, you can see I've got a function of one variable divided by a function of another variable. So this differential equation is a so-called separable differential equation. Okay, so let's just use a little bit of manipulation to separate the variables and integrate. So what I can do is bring that 2y over to the left-hand side. Okay, so let's just multiply both sides. Sorry, let's just bring the y over. I'll leave the. Shall I bring the y? Yeah, let's bring the 2y over. Okay, so I get 2y to y dx equals minus x. Now, if I integrate both sides of that bottom line with respect to x, then see what happens. Now, you can see that this dx is just going to cancel out. So, essentially, I've got two integrals to do. If I integrate the left-hand side, I'll get something like y squared. If I integrate the right-hand side, I'll get something like a half x squared. Now I'll put a constant of integration in. Okay, you could put a constant of integration on both sides. It's not necessary though. Now, what I'm trying to do here is solve for the unknown function y equals y of x. Okay, I want to come up with some solution, some representation for the unknown function y. Okay, so if I just rearrange this a bit, now, the constant c in this particular case must be non-negative, okay? Because you've got a y squared plus a half x squared, that can't be negative, right? So any constant of integration must be non-negative here. Okay, well, actually, that's an implicit way of writing the solution y. I could rearrange it and take square roots and things like this, but this is okay, and this is quite common with these kinds of problems. We'd like to get y as a function of x, but it's not always easy. So think of this as an implicit solution. Okay, now I'll come back to that in a little while. Let's have a look at question B. Question B gives us a little bit of extra information about our problem. We know that the solution we're chasing has value 1 when x equals 0. So this kind of information here is known as an initial condition. Okay, so I might be able to find this general constant with this piece of information. Let's see if we can do that. Okay, so if I plug in x equals 0, y equals 1 in here, then, so let's call this double star. Okay, so I get 1 squared plus a half times 0 squared equals c. So what should my constant of integration be? Well, it should be positive 1. Okay? But I'm still not quite satisfied with my solution. Okay? Now, if we just look up here for a second, what kinds, so forget about this for a second, what kinds of curves, if I draw these in the xy plane, what kinds of curves will I get for non-negative or positive values of c? Ellipses, right? Ellipses. Now, I don't, like the ellipse, each ellipse will have a top arc and a bottom arc. If I rearrange this boxed equation to try to make y the subject, I'll get something like that. Now, which form do I want? Do I want the positive square root or the negative square root? Well, there's only one of those two curves that pass through this, that satisfy this initial condition. It's the positive one. Okay? So what's our final answer? Okay, now this, you can see in the bottom right-hand corner, this solution won't be defined for all values of x. It'll only be defined for a limited value of x. Okay? So that's a good overview of how to solve these problems. Usually, what we do is we actually, you can actually bring the dx up there in one step. Okay, you can see it and then integrate. Okay, the only reason I've done it a little bit slower over here is to show you some justification with cancelling the dx's. So actually what you would do if you were doing this problem, you'd bring the dx up here, the 2y up here, and then just integrate both sides. So if I wanted to break it down to 2 steps, you separate the variables, the x's and the dx's on one side, y's and the dy's on the other, and then you integrate. Okay? You with me? Okay, so let's look at the bigger picture. So like I said, separate the variables and integrate. Now, when I mean separate the variables, when I say that, I mean you want to do that using multiplication or division. And sometimes some algebraic manipulation is required to solve the ODE, as we saw. If an initial condition is known, then the constant of integration can be determined, at least for simple problems. So here are a couple of examples for you guys to try. The solutions are down below, the answers are down below. So have a go and see how you go.